All right, let's run through.
1 second. Yeah.
All right, let's run through a quick degrees of unsaturation calculation, and then we're gonna run through some other reactions. So let's look at A. What about A do I need to look out for in my calculation of degrees of unsaturation?
You said what are we looking for?
Yeah. What about A? There's some atom in A that I have to make.
Oh, it's a group 5.
Group 5, good. I need to make an exception for that, right? So when I calculate HREF, I need to add 1 to it because I have a group 5 atom, right? So HREF is just going to be 2 times 6 plus 2, which is 14, plus 1, which is 15. And again, I'm adding plus 1 for that group 5 atom, nitrogen. So it'll be 15 minus 13 over 2, which equals 1. What does that mean for C6H13NO? What does that mean in terms of the degrees of unsaturation? What does that mean?
You have 1 double bond.
Or
1 ring.
Or 1 ring. So if you had to propose a structure, right, I would go for 1, 2, 3, 4, 5, 6 carbons, a double bond here. I just throw in an OH and throw in an NH2, and that should satisfy. 1, 2, 3, 4, 5, 6 carbons. Each carbon, this is a CH3. Grab it so I can move it over. This is a CH3. There's a hydrogen here, 1 here, 2 here, 2 here. So 3, 4, 5, 7, 9, 10. I'm missing 1. 11, and then 13. So that structure would satisfy that molecular formula. What about the next one? Actually, let's just do C.
I have a quick question.
Go ahead.
I'm sorry. So I was moving slow, but so why did you add the +1 for the N?
Anytime you calculate degrees of unsaturation, if you have a group 5 element, you always add 1 to HREF. Because remember, the formula is HREF minus H molecule divided by 2. And HREF is always 2N plus 2. Right? So if I have a group 5, I have to add 1 to that. Now, you might see it in a book, in your book or somewhere else where you subtract 1 from H molecule. Right? If you have group 5, and then you add 1 to H molecule if you have group 7. But the way that we discussed it here, you add 1 to HREF.
Okay.
All right. Let's do C. What would you do to C? This was A. Is that right? I have 2 nitrogens, so I'm going to add 2 to HREF. If I had 10 nitrogens, I would add 10. It's 1 for each group 5 atom. So HREF is 30, and it'll be come on, pen. 30 minus 10 over 2. So 10 degrees of unsaturation. It's a lot, right? But it's doable simply because if you have 13 carbons, you could consider that as 2 6-membered rings together. That'll give you 10 of your carbons right there. So if I fuse this, if I were to propose a structure for that, all right, I could do this. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 2 degrees of unsaturation. And then if I put double bonds in, so that's 2 rings, that's 2, and then 1, 2, 3, 4, 5 double bonds. That's 7. So I have 3 degrees of unsaturation left, right? And I still have 3 carbons left that I can use, right? So I could,
Dr. Russell,
yes.
how you knew where to start counting?
What do you mean? Oh, it doesn't matter.
Okay.
Yeah. I just, the 2 rings together, you can start counting anywhere, but it's going to be 10 carbons total. And I still have 3 carbons left. So I could put another double bond there. And then I have 2 nitrogens. I can do this. I got 1 oxygen. Oh, actually, I got 4 oxygens. Hold up. I don't know how to fix that. So let's see if I used up all my degrees of unsaturation. So 13, 20, 30, 10. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. I need 1 more degree of unsaturation. Where could I put it? How many carbons I got over here? 1, 2, 3 carbons. I need 1 more degree of unsaturation, and it can't be less. Oh, I could do that. Yep. This is a kind of a tricky one. We'll do that. And that'll satisfy all of them because I think that'll satisfy it. Oh, I need to put that double bond back in. So I'm gonna do that. Yeah, that's a little bit tricky, but it's doable. You just have, again, this is all like trial and error. As long as it's a valid Lewis structure, then you're good. But that'll satisfy the 13 degrees of unsaturation, or the 10 degrees of unsaturation for that one. All right. You can do these. So I'm gonna label that as on your own for you to finish those. Let's look at number 2 down here. It says rank the carbocations below in order of increasing stability. What does that mean? And how do we know what's the trend for carbocation stability?
Most substituted to least substituted.
Okay, I'll take that. So tertiary is going to be the most, right? And that's the best. Secondary, primary, and then the worst is methyl. So you look at those carbocations, which one is the most stable?
Would it be the second one?
The second one is tertiary, right? And it said most stable is 3, least stable is 1. So this is a tertiary carbocation, so that's going to be your most stable. And then your least stable one is going to be which one?
The last one.
Yep, it's primary, right? And then this is secondary. All right, let's go to, I'm gonna skip over that. We'll come back to that. Let's answer this question. A mechanism
Can you
is,
go back up a little bit real quick? Okay, thank you.
all right, let's go to, I'm gonna come back to this halogenation mechanism. It says mechanism is considered stepwise if what?
Isn't it A?
Yeah, it's stepwise if it happens in multiple steps. If it happens in a single step, then it's not stepwise, right? What's the term for that?
Concerted.
Concerted. And the next question it asks about this reaction energy diagram. It says it most likely corresponds to a reaction that is what? How do you distinguish between a stepwise reaction and a concerted reaction?
A transition state.
You're close, but every reaction goes through a transition state. What about there's something that could come after the transition state? Think about it. If I go from starting materials to here, and then I go from here to the product, what is this space between those two steps?
Intermediate.
It's an intermediate. That's how you distinguish between a stepwise and a concerted reaction. A concerted reaction is not going to have any intermediates, right? It's going to go straight from reactants to transition state to product, right? A stepwise reaction will have at least another step between the reactants and the products. It will have at least one intermediate. Right, so for this energy diagram, what do you think? Stepwise or concerted?
Concerted.
Concerted, right? You only have one step to get from reactants to products. All right.
Dr. Russell, can you go back to number 2? I can't.
This one?
Yes. So how did you know which one was like primary, tertiary, secondary? How did you know that?
About to throw a shoot through the screen, but not yet. So this carbon right here, it's got 3 carbons attached to it. That's how we listed it as tertiary. This carbon only has 1 carbon attached to it, so it's primary. And then over here, this carbon, where the charge is, has 2 carbons attached to it. So it's secondary.
Okay. Yeah. Okay. Thank you.
All right. Don't forget the duck now when I throw the shoe. All right. Let's go to here. So which of the following reactions shown below will the reaction energy diagram best represent? Now look up top at the diagram. What do you think? You can take your time, look at the reaction, read it carefully, and then answer it.
Would it be 2?
2. Yep. It doesn't go
I
through
only
intermediate.
concluded that from it saying it does not proceed through intermediate.
But yeah,
But
that's the purpose of that information.
okay.
So you drew the right conclusion based on the information that you had, because otherwise you would have to work through the mechanism for each one, right? But if it doesn't go through an intermediate, that's a dead giveaway that it's a concerted reaction.
If that wasn't like set up like that, what's another way I'd be able to tell to
Go
answer that question?
propose a mechanism for each one, and when you do the mechanism, then you'll see, like for the hydroboration oxidation, that's not it's stepwise in the sense that it has more than one step, but both of those steps are concerted, right? So the BH3, that's a reaction all by itself. It has nothing to do with the hydrogen peroxide and the sodium hydroxide. It's a totally separate reaction. So there's no intermediates per se in either one of those steps. So the whole thing is considered stepwise. But you would have to, if you didn't know that it went through an intermediate or didn't, then you would have to propose a mechanism for each one. Oh, while we talking, y'all make sure you vote if you haven't. I know some of y'all are at home doing school virtually. Make sure you go vote. I know that's random, but I just saw something on television that made me think about that. All right. So yeah. So if you have no idea whether it's stepwise or concerted, then you'll have to go through the mechanism. All right. Let's do these A through C. Let's start with A. What type of reaction is that, and what's the product? These are your reagents. You got an alkene. Keep in mind, all we worry about is alkenes right now. So you got an alkene, you got osmium tetroxide, NMO. What's the outcome? Right? Osmium tetroxide is a way to turn alkenes into diols. And the alcohols that you make in the diol have to be cis or syn. Was that right?
Yes.
All right. Let's do the next one. What happens when you take a alkene and you react it with MCPBA?
Oxide.
Epoxidation. Good. Kind of sloppy. Was that right? There's a lag between my iPad and the screen, but yes or no? Right, it's an epoxidation. What's another way I could do epoxidation?
With peroxide?
Good. Hydrogen peroxide. Very good. What about the last reaction?
It's a halogen.
Good. Is that what we get? But OH and bromine are opposite to one another. Is that right?
Dr. Russell.
Mm-hmm.
So I have a random question. So on an exam, is it more questions that's asking like for the direct product or like the mechanism to get to that product?
Both.
So it's like evenly distributed in the exam?
I wouldn't say even because it's not evenly distributed, but
Okay.
there are both types of problems in there.
All right.
Mm-hmm. All right, let's go to number 7. It says oxymercuration occurs with blank. Anti-stereochemistry, syn stereochemistry, trans stereochemistry, or unpredictable stereochemistry.
I think it's sand.
Yeah, it is. Remember, we talked about this. When you add oxymercuration, at the core is adding H, OH to a double bond. But the H and OH both add to the same base, right? So it's syn. What about the regiochemistry?
Markovnikov.
Yeah, it's Markovnikov regiochemistry. Good. All right. Now let's look down here. It says choose the best reagent from the list below for carrying out each transformation. Place the letter of the reagent on the blank, blah, blah, blah. Let's start. Ooh, we haven't covered this yet, that part. But let's start here. What set of reagents would you use for that to convert that alkene into the alcohol you have on the other side? Need some Jeopardy music. Let me see if I can. Which set of reagents would do that? add H and OH, and add the OH on the least substituted carbon. And we just did this the other day, Wednesday. The exact same problem too. It's a hydroboration. Is that right? All right, what about the one above it?
That'd just be the opposite, right?
Which reaction is it? You're right, it is the opposite. All right, these are your choices up here.
The HG one. D.
Mercury.
Mm-hmm.
So it's this is an oxymercuration. And this is hydroboration. All right, what about the top left first reaction right here? How do I convert alkenes into carbonyls?
Ozonosis.
Good, close enough. Ozonolysis.
Oops, my bad.
You're all right. So it's an ozonolysis, right? And remember, that's like when you treat it with ozone, it's like basically taking the alkene and cracking it in half, and putting the oxygen on each one of the carbon on each one of the alkene carbons. Right. So you basically are splitting this alkene here, and each one of those carbons becomes a carbonyl. All right. The last reaction here is called, it's a name reaction, right? It's called a Simmons-Smith reaction. I think it was in that last video I sent you. Right. It's called a Simmons-Smith. It's a way to turn alkenes into cyclopropanes. A cyclopropane, cyclo is how we indicate that there's a ring present. So a cyclopropane is a 3-member ring. Come on now. It's a 3-member ring. And so you can see right here, you have a 3-member ring in the product. And if you look at the reagents, it's diiodomethane. Let me write that down here. And then zinc with copper. Right? So basically, this carbon right here gets inserted into that alkene. Right? So it's almost like making an epoxide. But instead of oxygen, you put a carbon between those two carbons in that double bond. I think this was in the last video I sent out, because I know ozonolysis was in there, and I think the Simmons Smith was the last reaction in there. Right? Questions? Any questions so far about anything we've done? All right. Let's go to number 10. We're going to skip the top one. I'll tell you about it, but we'll do it after we do the next one. What kind of reaction is that second reaction right here? And what's the outcome? You got hydrogen and platinum oxide as a catalyst. Platinum oxide as the catalyst. And you're doing it in ethanol as the solvent. What is that hydrogen going to do to the alkene? Right? This is an example of a hydrogenation. So you basically add hydrogen to both carbons, one hydrogen to each carbon in the alkene. So it takes alkenes to alkanes. Did we just do this Wednesday? What's the
Yes, I
other?
think so.
Yeah, what's the other catalyst that you could use besides platinum?
Palladium.
Palladium. Good. Good. All right. We're gonna actually skip this one. The per hour date cleavage. We'll skip that. All right. This is for the reaction wheel. Let's see if we can figure out what happened. So let's start at 12 o'clock. See that this asks you to pick the reagents to take you from 1 to 2. What happened going from 1 to 2?
You lost the double bond.
Lost the double bond. So out of those reagents, which one of those is able to do that? Right. The peroxide would give you an epoxide. Ozone would crack the double bond in half, right? And give you 2 carbonyls. The sulfuric acid and mercury sulfate, that's like a type of oxymercuration. So what's left? Hydrogen and platinum oxide. Same reaction.
Wait, Dr. Russell, why are you crossing out the ones you crossed out?
I didn't cross any out. I just highlighted
Okay.
the correct answer. It's the same reaction we just did up here. I started with an alkene, and then the product the alkene became alkane.
Okay.
All right, so that's a hydrogenation reaction. All right, let's do, it says 1 to 3.
Is that C?
It's C, right? It's a Simmons Smith because you started with an alkene and then you end up with a cyclopropane. And it's always the same set of reagents. The Simmons Smith, you can't add more than one carbon. So that's why it's always that diiodomethane and zinc. All right, what about 1 to 4? What do you think? What did I do?
You made carbonyls.
Exactly. From the alkene. And so which set of reagents am I going to use for that? KOH won't do it. Hydrogen,
C.
yeah, it's an ozonolysis, right? We took this ring and we cracked it open, right, at the alkene. So each carbon in the alkene became a carbonyl, right? And if you ever, again, if you have a hard time seeing that with the ozonolysis, you can always put an oxygen here. Oh, sorry, I gotta make my pen smaller and zoom in more. You can put an oxygen here. You can put an oxygen there, right? And so both of those are gonna become still ugly. So both of those are gonna become a carbonyl. So you'll put oxygen, oxygen, and then that way that's how you know where your carbonyls are gonna be, right? That's a good way to think about it. All right. So we know that's an ozonolysis to give me 4. And 1 to 5, what is that?
Is it osmolation?
Osmolation. I took an alkene and I turned it into a sandiol, right? So it's an osmolation. All right. Is everybody okay with the? Well, let me not ask them. Is everybody okay? Well, I'll ask. Is everybody okay with the ozonolysis? Because I know that can be tricky when it's in a ring. All right. Scroll down to, actually, that's it. Wow. Guess that's it. We didn't do this reaction right here. Propose a mechanism for halogenation. But we can do that quickly. What's the first step?
The double bond acts as the nucleophile.
Yes. It's gonna actually attack the chlorine, isn't it?
Yes.
Mm-hmm. Somebody been studying. Good. We're gonna attack here, boom, like that, and we're gonna break that chlorine bond. So then we end up with this intermediate, not that. N. Chlorine, a negatively charged chlorine here. What happens to the intermediate? Does it stay like that?
It immediately attacks the carbocation.
Who was that?
Amaria.
Good. Thank you. You're absolutely right.
Thank you.
So you close that up. Remember, we call this chlorinium ion, right? Because the chlorine has a plus charge on it, right? And so that, I'm gonna make it wedged. All right. So that intermediate, now I'm gonna attack it with the other chlorine. What's the hallmark of this reaction? Look at the product. What's the relationship between the two chlorines? Are they trans or are they cis to one another?
Isn't it, sis?
Cis would be on the same side. You see how one of them is dashed and one of them is wedged? So that means they're opposite to one another. So they're trans.
Oh, okay. I was looking at the wrong thing.
That's
Yeah,
okay.
okay.
That's
Sorry.
okay. All right, so now this is going to attack here, right? Boom. Pop that open like that. And so then you end up with your product with the two chlorines opposite to one another. They're always trans. trans. Always trans. All right. I'm actually going to stop and let y'all go early. The exam will be posted shortly. I think it's set to drop at noon. And you got until Sunday, 11:59 to finish it.
Dr. Russell,
Yes.
I have a question. If you scroll up to number 1,
Mm-hmm.
like the ones that we're supposed to do on our own,
Yeah.
like up a little bit. Like for the B, I was solving it, and when I was trying to solve for the degrees,
Mm-hmm. To my right here.
your screen is dark.
Whoa. Hold up. Something happened. There we go. All right. It was the first one, right?
Mm-hmm.
Right here.
No. Like number 1, like calculate the degree of unsaturation. Yeah. When I
Yeah.
was doing B, I got an odd number over 2. Is that supposed to happen or no?
Mm-mm. It shouldn't be odd. So you have, what did you do? How did you solve it?
So I did the 2n plus 2. So I did 2 times 16
Mm-hmm.
plus 2.
Mm-hmm.
And then I get 34. And then since the n is there, I
How many?
add 2.
Mm-hmm.
I add 2 and I get 36.
Mm-hmm.
And then I do the 36 minus
Minus 1, because you got a chlorine. So it should be 35 minus 13.
Oh. Okay. All right. Thank you.
Yeah. Those. Remember, you got a chlorine. You got to subtract 1 for each chlorine. If you have a group 5, you got to add 1 for each group 5 to HREF.
HREF. Okay. So then, yeah. Okay. That's an even number. Thank you.
Mm-hmm. Any other questions about anything? No? All right. I'm going to stop sharing and I'll stop recording.